Okay, and we're recording. So welcome back, everybody. Let's see, third week of classes, but it's our first Monday morning. Okay, so last time we left off, we were talking about lines and planes, and there's a category of questions involved in when you're talking about lines and planes, and that is what we call distance problems. And so this book very nicely puts them all into a single subsection. So I'm going to talk through sort of the strategies of how to compute various of these distance questions, and they're going to come up in the homework exercises pretty significantly. Okay, so let's suppose you have a point and you have a line, and you want to compute, as it says here, the distance from a point to a line. So we want to compute this distance right here. How would you compute that distance? So there's a couple of different ways that I'm going to show you how to do this. When the first solution I'm going to show you is makes use of projections. So keep in mind, you start off with a point, but you can also just pick some other point on the line. Any point doesn't matter, and subtracting then gives you a difference vector there. Okay. All right. Now, again, this is not what we need, but next thing we can do, we can take the projection of that vector down to the line, right? And we have formulas for projection. We talked about that previously. Again, also not what we want. However, the difference, W minus that projection, that difference is this vector I'm calling D, and notice that that vector D, its magnitude is the distance that we're looking for. So, real clever little move. Subtract, project, and subtract again. Okay. Any questions about this strategy here? Everybody's happy? All right, now here's a totally different way to answer the exact same question. This one's a little weirder. Strategically, though, what I really like about this one, it uses a method that's actually used in several places. This is not a completely one-off strategy. If you want to compute something, sometimes the best thing to do is to start by computing something else that you're not interested in. And in particular here, I'm going to look at this parallelogram. That is not what we're interested in. But I'm going to compute that area. And the trick is, compute it two different ways. We'll talk about the details of each of these two computations. But sometimes, if you compute something you don't care about two different ways, what'll happen when you realize that, well, I computed it two different ways, therefore my two results must be equal. That sometimes makes the thing that you're interested in show up as part of an easy equation that you can just solve for. It's a really clever move, right? Very clever move. Anyway, let's see the details now of how these calculations work. First, keep in mind we're talking about this area right here. The first thing I want to compute here to get that area is to observe that it's that distance, whatever that is. Don't know how to compute that yet, but nevertheless, whatever that distance is, times this base here, and that base is the magnitude of this projection vector. Again, we talked about that in the previous example. Okay, so blue times green, that gives me the yellow area. So that's one calculation of the thing that I don't care about, namely that area. Okay, next calculation of this thing that I don't care about, namely the area, is to recall that we know cool facts about the cross product, and that vector cross that vector, right? Cross product of those two vectors, its magnitude gives us the area, right? And I don't actually need the cross product particularly, but its magnitude gives me that area. Also, that I don't need, right? I don't really intrinsically care about the area. Yes?
I just want to know, like usually the area of parallelogram, isn't it like the perpendicular to the base, right?
Mm-hmm. Yep.
So why is it the diagonal in this case when we're multiplying the base? Right?
What? No, it's
in the d into the magnitude. This one.
Yeah, so the reason there is because where this vector came from wasn't arbitrary. This vector is the projection of this vector. And so in the act of projecting it, that sort of makes this automatically a right angle. Does that make sense? So this again, the point is this is not an arbitrary vector. Had it been like, that vector, then yeah, it wouldn't be, it's not the diagonal. The fact that it's a diagonal air quote is coincidental and irrelevant. Yeah, totally. Yeah. Everybody good? Cool. Okay, so we've done two separate calculations. We've computed this area once as base times height, once as clever fact about cross products. Therefore, these two calculations that we've done give the same answer, and therefore we have a handy formula for this distance d that came up as in one of those calculations. It's a real slick move. By the way, this is a good strategy to remember. At some point in the future, you may be interested in computing something, and it's not clear how you'd compute it, but if you can involve it in a calculation of something else, right, then that's a foot in the door that can lead to answers here. Okay. Alrighty. So, moving along. Okay, how to find the distance between parallel planes. Now, you got to keep in mind when we're talking about the difference between two planes, that does not mean just take any two random points and compute that distance in between the two random points on the plane, right? You can tell that distance is different from that distance, which is different from that distance, which is probably the one we want, which is different from that distance, right? I mean, arbitrary points doesn't cut it. So when we say the distance between parallel planes, what we mean the perpendicular distance, right? The distance along a line segment perpendicular to both sides. All right. So how to compute that? Wonderful little observation is that distance is literally the component. It's the component of any displacement vector between the planes in the direction of, whatever is the direction perpendicular to the plane. So just take your normal vector. So, I mean, this one, sometimes they just work real quick. So the big point here is just to recognize that the distance in question is an easy component. How are we doing on that one? Everybody good? Nice little trick, yes.
Is it okay if we, for example, like with the starting place as b, and then we have the normal vector, right? And then we just plug in that into the bottom plane's equation. We find the point, and we find the difference between the intersection. Right?
Sounds to me like you're citing a formula. What I'm looking for is an argument, right? So I'm going to have to ask you why that would be true. You see what I'm saying? Right? So there is a formula. You're right. There is such a formula, but I don't want you to memorize formulas. I want you to make arguments. And the reason my argument works is because picture and you see that this clearly is the case, right? Plugging in one point into an equation for another. Okay, why? What are we doing? What does that mean? You see what I'm saying? Yeah. Does that make sense to everybody? Right? Okay. Yeah. Right. Okay. Alrighty. Okay, the last one, and this is a really tricky one. And again, I want to remind, I think I may have said this before, but there are a lot of instances in math of clever little calculations that I never would have thought of myself. I really would not have thought of this. I don't know, maybe, possibly. But you don't want to ask yourself, would I have thought of this on my own? Ask yourself instead, now that someone has showed you the trick that I'm about to show you, can you follow the argument and make use of it in the future, right? And there are a lot of such instances. This is one of them. This is an extremely clever move, and don't hold yourself to the, I think, far too high a standard of would I have thought of this extremely clever trick on my own. Okay. All right, so skew lines. So skew lines, you may recall from high school geometry, are lines in space that are not parallel and that don't intersect. Right? It's what you might call a worst case scenario for lines. They have nothing in common. Right? Okay, so how would you find the distance between two skew lines? Well, again, you have to keep in mind that there's a bunch of, distances that you might think as being relevant, but that aren't. I mean, here's a point on one of the lines. Which of these distances would you call the distance to the other line? And, if you decide that this is the point on the other line in question, then why would you necessarily choose that point? Why not any of these points? There's a bazillion different pairs of points we could look at. How do you know which one is the one that gives the actual distance? And the clever move is to realize, and I'm going to show you how to do this momentarily, but whenever you have skew lines, there are parallel planes that contain those two lines. Now, again, I owe you an explanation of how to find those parallel planes. All right, well, once you have two parallel planes containing those lines, I think it's a pretty easy sell that the distance I'm looking for, this distance between the two skew lines, perpendicular to both lines, that distance is, it's the distance between the two planes. Right? And we already know how to find the distance between two planes. That's this move up here. All right, so strategically, that's the big trick. So now we just have to figure out how are we going to find these two parallel planes. And a really clever idea. If you look at the direction vector for the first line, note that direction vector, being parallel to the first line, is also parallel to both of the planes. Right. Likewise, the second direction vector for the second line, that is also parallel to both planes. And now I've got then two vectors that are parallel to these planes, and therefore their cross product is perpendicular to both planes, and therefore that cross product can be a normal vector. And once you got the normal vector, again, we know how to find equations of planes, n dot x, n dot x naught, and all that business. So, real clever move. Again, wouldn't have thought of this myself, but real neat argument. Okay. All right, so that's what we've got for section 1.5. We're moving on now. Keep in mind we've already done 1.6. We did that at the very start of class for prerequisite reasons. And now we're going to move on to 1.7. And so new coordinate systems. Some of y'all may have seen some of these coordinate systems previously. That's great if you have, but I don't assume that you have. So I'm going to go through all this stuff. Usually when we talk about points in the plane, we talk about their rectangular coordinates. And rectangular coordinates are exactly what you think they are. They're the coordinates x and y. Right, so these are the rectangular coordinates for a point in space. And for every point, in the plane. For every point in the plane, we have correspondingly rectangular coordinates, and vice versa. For every pair of rectangular coordinates, we have a point in the plane, and it's a one-to-one correspondence. So another way to say this is that rectangular coordinates are unique. They're unique because for any of one, there's exactly one of the other, and vice versa. Okay. Now, sad news, the new coordinate systems that we're going to talk about are not unique. It's very frustrating. For example, polar coordinates, some of y'all may have seen polar coordinates before. The polar coordinates of a point in the plane are not unique. There are multiple different sets of polar coordinates for a given point in the plane. So very frustrating. This is something that we've been spoiled with rectangular coordinates being unique, and we talk about the x coordinate and the y coordinate because, well, again, there is only one. So you're going to have to kind of let go of that luxury when we go on to these new coordinate systems. Another couple of cool facts is what I'm going to call algebraically convenient. One really convenient algebraic fact about rectangular coordinates is that the coordinates are the coefficients in a linear combination of the standard basis vectors that gives rise to that vector. Right? So this point, x comma y, is a linear combination of E1 and E2. Oh, color choices. All right, that purple point is a linear combination of the standard basis vectors, and the coordinates are the coefficients. Very handy. And unique to rectangular coordinates. And then likewise, there's these. Look at how nice this is algebraically. If you take a linear combination of vectors described in rectangular coordinates, you can just take the corresponding linear combinations of their individual coordinates. And just very handy, and also a luxury, also not true in other coordinate systems. Okay, so as we go through these new coordinate systems, heads up that everything's different and less convenient in most cases. Okay, so now y'all again have probably, some of you may have seen polar coordinates previously. I'm going to give you a slightly different point of view perhaps than you may have seen. I like to think of them as relating to a function, that there is a function from what I'm going to call the r theta plane into the our usual xy plane, and think of the polar coordinates then as the inputs to this function. So if you give me an r and a theta, which you could think of, I suppose, as a point in the r theta plane. Right? Given the r and the theta, that r and theta will tell you what direction to go, and I'm going to say air quotes, how far to go in that direction. Right? Now, just, real quick before we get into the nitty-gritty, pretty believable that this would help you describe the location of a point. If you want to get to a certain point, just tell me what direction should I go from the origin and how far should I go in that direction, and then boom, that puts me on that point. Okay, fine and dandy. So what's with the air quotes? I say how far. The problem is how far suggests a distance which suggests positive. And in fact, there is no rule that says that r has to be positive. Side note, we are going to choose in the future, for good reasons that we will be able to motivate at the time, we will eventually choose most of the time to require r to be positive. But until we get to where we have good reason to do so, we have no incentive, no reason to make such a restriction right now. So for the moment, r is perfectly allowed to be negative. No problem. And so what do I mean by how far? If r is negative, I'll just go backwards. Right? So if r is negative, then you do that. Alrighty, how are we doing? Everybody with me? Okay, easy trig. I'm going to leave the trig to y'all. Make sure that you can do the trig here. Of course, we're looking at this right triangle, and if you think about how you would find x and y on the basis of this right triangle, what you'll find is that x is our cosine theta, and y is our sine theta. Okay. Alrighty. Okay, so not unique. Sadly, it's just not. So, for example, here is a point in the plane, and maybe the easy way to think of that is that there's a certain angle here. Why don't I use colors here? There's a certain angle describing what distance I should go. Or what direction I should go, and then I'm gonna say that this point is a distance 5 from the origin. So I want to go then 5 in that direction, and go in a distance of 5 in that direction. Sure enough, puts me at that point. So you could say that these are polar coordinates for that point, but they are not the only polar coordinates for that point. Now this is going to seem a little goofy, but notice I could, I suppose, add 2 pi to the angle. And think about what would happen if I added 2 pi to this angle. Well, instead of going that direction, I would be going, exactly the same direction. Right? Here, let me do this where it's a little bit more visible here. So adding 2 pi to the angle, in fact, as far as the xy plane is concerned, adding 2 pi to the angle does not change the direction that we're going. So you could say 5 comma theta, but you could also say 5 comma theta plus 2 pi. Everybody see the problem there? Uniqueness just not going to happen. And then, of course, there's the other option of instead of adding 2 pi, I could add 1 pi. Let's see what happens if I add 1 pi to the angle. Adding 1 pi to the angle gets me going in exactly the wrong direction here. Let's see here. Gets me going in exactly the wrong direction. And the thing is, if I want to end up here, and if I'm going exactly the wrong direction, notice I can just go, let's see here, what are we doing for, blue. I can just do negative in that direction, right? So I'm going in that direction by a negative amount. And again, it gets me right back to that same point. Everybody on board? All right, so lots of non-unique issues with polar coordinates. Okay, now just a couple of warnings I want to give you about dealing with polar coordinates. Sometimes people will write polar coordinates without giving any indication that they are in fact writing polar coordinates. And so, for example, if you see 2 comma pi over 6, a lot of people will look at the pi over 6 and say, oh, pi over 6, that's an angle. So that must mean that we're talking about that angle pi over 6, and then I'll go a distance 2 in that direction, and that gets me to what I would interpret this point as. It's that point in the xy plane. And that seems reasonable. Here's the problem. If you write 2 comma pi over 6, let's not lose sight of the fact that while this does look like an angle, it's also a perfectly valid real number, and it could be y. There's nothing wrong with thinking of pi over 6 as being a y coordinate. It's a number. Y can be any number, so it could be y. And then likewise, the 2 would then be the x. And now we're talking about this point, which is a different point. So this is just look. The problem here is in just you have to be careful of sloppiness. And so my advice is, in any situation where the context does not make it perfectly clear what you're talking about, just clarify. It's so easy to do. All you have to do is just say r comma theta equals, and now there's no ambiguity at all. Right? Clearly then, this number is r, and this number here is theta. No ambiguity at all. So just heads up, if you're reading the book, and if the book commits this little micro crime, then you have to look for context clues, but they really should be more clear. Okay. All right. Here's another warning. Some students who have seen polar coordinates in the past, a little bit too fast and loose with the algebra. And there's some easy mistakes, little landmines you can step on and get in trouble, and if you're not careful with this kind of thing. Okay, so looking at the definition of polar coordinates, it's very easy to persuade yourself that r squared is equal to x squared plus y squared. And a lot of students will want to solve for r and say r is the square root of x squared plus y squared. But that would imply that r is positive, which it need not be. So careful about that. Likewise, easy trig tells you that as long as x isn't 0, we can define tan theta. Or not define. We can note that tan theta is y over x. Right? Easy little trig of the original definitions. And a lot of students would like to solve for theta. Theta just arctan y over x. What's wrong with saying arctan of y over x? Problem, arctan is always between negative pi over 2 and pi over 2. Theta has no such constraints. Right, so look what happens if you're a little too sort of quick about this, and I'm going to start by looking at this point right here, -1 comma -1, rectangular, -1, -1, and now you can plug into these formulas up here, and out come these facts, true facts, right? And a lot of students will think, oh, well, this means that R is the square root of 2, and this means that theta is pi over 4. Right? If you were to take the, R is, take the square, solve for R, solve for theta, that's what you would get. And what does that tell us? Well, if we look at square root of 2, comma, pi over 4, that gives us this point right up here, and that's wrong. That's just wrong. Right? I mean, it's just not, it's 1 comma 1, that's not the same point. Everybody see what happened? So, very dangerous. Don't fall for the tempting convenience of, I just solve for R and solve for theta. No, what you have to do, really, is look at your options. Right? And again, reminder, we're at this point, -1, -1. And so R could be, well, it could be either one of these. I don't know, it depends, but these are the candidates on the table. And theta could be pi over 4. Well, to be fair, it could be also plus any multiple of 2 pi. But it could also be 5 pi over 4 plus any multiple of 2 pi. Right? So, all right. So now again, still be careful. Having listed all the options, think about how you pair them up. It's tempting to kind of pair, well, these are the most convenient numbers, so I'm just going to choose those. But again, that puts you back at the wrong point, right? So what you have to do is actually, you have to think about the geometry. You have to think about, okay, where is my point, and what are my options, and of the remaining options that I have, how do I get to this point? And one thing you can do, of course, is think about that angle, 5 pi over 4, and then go a positive amount in that direction. So you could say root 2 comma 5 pi over 4. Perfectly fine. Right? Or, if you want, you could say that direction. And then, of course, you see from the picture, thank you, picture, that you would have to go a negative amount in that direction to get back to, again, that correct point. Okay, so careful, right? Think about the geometry of the picture. Don't rely on just formulas. They will give you wrong answers. Okay. Pausing. Questions? Everybody buy it? Yes. Oh, sorry. Was that a... Okay, yeah. All right. All right. So something to be real careful about. All right. So, let's talk about equations in polar coordinates. Sometimes they're easy. For example, if you have r equals 3, okay, well, that's just straight up telling you that it's a circle. It's straight up telling you that we're looking at the set of points whose distance from a fixed point, namely the origin, is constant. That's, in fact, kind of, I don't know, is that the definition of a circle, maybe? Right? It's a freebie. But, of course, you might not have noticed that. If you don't notice, let this be a nice example of a strategy you can use in more general cases. But square both sides, and having done so, notice that the left side of the equation turns into something that I can immediately translate into rectangular coordinates. And the right-hand side is a constant, so I don't need to translate it at all. So, slick move, and what I've done is taken my new polar equation that I didn't have previous familiarity with, and I've turned it into rectangular coordinates where I recognize it. Oh yeah, high school algebra, I remember this is a circle. Yes?
But this only works if the r is positive, right?
No. It works fine if r is negative. Yeah, no problem. Because let's say r equals -3. Right? If r is equal to -3, then in every direction, I'll need to go a negative amount in that direction. And as the angle turns, you just trace out the exact same circle. Yeah. Is that cool?
Yeah.
Everybody else? Okay. Alrighty. Let's see here. Okay, yeah, so theta equals pi over 3. And again, you can make a direct argument about this one that, okay, theta equals pi over 3 means I'm talking about that direction. Apparently there's no constraints on r. R could be anything, and positive or negative, and that gives you this line. But again, if you didn't happen to notice for whatever reason, note that again, you can do algebra to turn the equation that you have into an equation that's easily converted. So here I'm going to take the tangent of both sides. And having taken the tangent of both sides, this immediately turns into y over x, and then I get again a familiar high school algebra equation and line. Okay. Sometimes, no such luck. This example here, it's just not, you're going to have a hard time doing algebra in such a way that this will turn into something that you can recognize. So sometimes you just have to plot points, brute force. Oh, kind of annoying. But anyway, here we go. Now, when I do point plotting on an equation like this, I like to break up the problem into chunks of angles. So, for example, I'm going to start here by looking at this range of values of theta, namely from 0 to pi over 2. Keep in mind, that's one of the participants in the equation, but it's not what I'm taking the sign of. The argument of sine is 2 theta. And 2 theta, as theta goes from 0 to pi over 2, 2 theta goes from 0 to pi, during which time r, namely sine of 2 theta, does this. It starts out really low, and then it increases, and then it decreases. So, knowing what r does over what range of angles, you can just come into the xy plane and just play it out, right? I know that as my angle goes from 0 to pi over 2, r is going to do this business here. And so it starts off, as the angle is low, it starts off with r being low, and as the angle increases, the r increases, and then as I approach the end, the r starts to go back down again. And that traces out a curve going like that. What do you think? Everybody see how I did that? Right. And let's see, now let's play through the second part of this. Let's see here. Get rid of all of the stuff here. Okay, so now I'm going to play through as theta goes from pi over 2 to pi. Well, keep in mind, theta is not the argument. The argument is 2 theta. And 2 theta then goes from pi to 2 pi, during which time r starts at 0, goes negative down to -1, and then it increases back up to 0. So now this one's a little weird, a little bit counterintuitive because the r's are negative, but notice for these values of theta, and let me sketch a few specifically. For these values of theta, starting off with our first value of theta, r is negative, and then as I go over, r gets more and more negative, right? And then as I continue over, r becomes less negative until it comes back to 0. And so the curve for this portion looks something kind of like that. Now, I think it's a nice exercise to keep going with this. I'm going to encourage you all to do that. Play through the remaining values of theta, and you can probably guess what's going to happen. This curve, in the same way that it kind of just continues through the origin from the first petal to the second pedal that we're making here. Likewise, what you'll find is that it continues through like that And then it continues through like that, and then comes back around on itself. And so it makes a little four-leaf clover. Does that make sense to everybody? Okay. All right. Okay. Sometimes you get lucky with the algebra. Now, this one here, you look at this equation and you might think to yourself, well, I don't recognize it, but I do see that I have r on the left, and I love it when I instead have r squared on the left, and there's a temptation then to just square both sides. And a reasonable thing that you could try, it just doesn't help in this case. R squared equals cosine squared. I don't know what to do with the cosine squared. Right, so the slick move here, this is, for your consideration, your possible use in the future, multiply both sides by r. You still get the r squared that you wanted. That converts so easily. But having gotten that by multiplying by r instead of by squaring, the right side becomes r cosine theta, which we also recognize. Right? So now this is trickery. Right? So that's, it's a neat move, and, you're welcome to use this anytime it might be convenient. Now we've got the equation in rectangular coordinates. It's all algebra from here. I do want to point out one thing about this algebra, though. A lot of students in this class, in previous instances of this class anyway, have forgotten how to do completion of the square. Right, so make sure that you, polish off your algebra skills and make sure that you're good with completing the square. That's what I did here to rewrite the equation like so. It is a little tricky, but it is an important trick to have in your toolbox. If you're a little rusty on how to do completing the square, no problem. Come to my office hours. I'll be happy to show you. I assume that the help room people can also help you with that if you schedule might be better. Okay, and then you move things around a little bit, and you get the familiar high school result of the equation of a circle. All right, everybody good with that? By the way, this one is worth remembering in addition to understanding, because it turns out that it's not rare for us to deal with circles that are that sort of tangent to an axis that going through the origin. So that comes up, right? So you definitely want to make sure to remember that r equals cosine theta gives you that specific curve. Very handy. And sometimes there will be a constant. Sometimes there will be like an a cosine theta, and just remember that makes this over here an a, and of course this an a, so just stretches everything accordingly. Alrighty, moving along. You can convert the other direction. Sometimes you have an equation given to you in rectangular coordinates, but you want polar coordinates. And, well, it's actually easier going this way because we can just straight up plug in, for example, see what I did here, y is r sine theta. And you can just plug that right in. And very often you don't even need to do any trickery. Now, I did do one little clever move here because it is a nice little time saver. Had I plugged straight in for x and plugged straight in for y and then multiplied it out, there would be a lot of terms, and then the Pythagorean trig identity would come up at some point. But neat move. Square it out first, and then notice the x squared plus y squared, that you don't need to write all that in terms of trig, and only then to rewrite it as r squared. We already know that x squared plus y squared is r squared. So, handy, right? There's just a little bit of a time saver. It saves us, 30 seconds, 20 seconds, something, to square it out first. And look for these kinds of opportunities to save yourself some time. Okay. All right. Again, another one that's pretty convenient. So another one to make sure that you remember. This is sort of the other way that a circle can be tangent to an axis at the origin. And this one involves sine instead of cosine. And of course, this number here is this number here, not 1 in this case. Anyway. Okay. All right. So that's polar coordinate. Yeah.
I just want to ask, I see you're dividing both sides by r, right? Before
Mm-hmm.
rather than taking the square root.
Yep.
What's the reason behind that rather than just taking the square root? Isn't that like eliminating the solution?
So let me make sure I understand. You're talking about this step right here?
Yeah.
So you're wondering why am I dividing by r?
Rather than taking the square root.
Well, see, if I take a square root, then I would have that, and that would solve, that would give r equals, but it would be r equals and then in terms of r. So that's not really solving for r is the problem. Does that make sense?
Doesn't like eliminate a solution or anything.
When I divide by r, that's right. You do. There is a problem whenever you divide by anything. If you divide by anything, you're responsible for the possible catastrophe of what happens if that thing was 0. Absolutely. So when I do this step and divide by r, I should consider then, wait a second. What does happen when r equals 0? Excuse me. And of course, no problem, right? That r equals 0, that comes about for certain values of theta anyway, and so it's something I had to worry about, but it actually wasn't a problem in the end. Yeah. Yep. That's a good point. Absolutely. Yeah. Okay. Cylindrical coordinates. I'm going to be really brief with cylindrical coordinates because it's pretty much polar coordinates. It's pretty much the exact same thing, right? So if you have a point in space and you want to talk about its cylindrical coordinates, the very first thing you do is you project into the xy plane. And once you're in the xy plane, then you're just, the first two of your cylindrical coordinates are literally r and theta for that projection. It's just polar coordinates. And then, of course, now we're in 3 dimensions. We need 3 coordinates, and the other coordinate is just, what is the z-coordinate from which I projected, right? What was this original z-coordinate that I effectively ignored by taking that projection? And, there you go. That's a set of 3 coordinates, and r, theta, and z will define a point in space. But you see what I mean when I say it's pretty much polar coordinates, right? So no surprise then, these formulas still true because it's still, morally polar coordinates and all of this stuff still true because all of that's the same. And I don't really need any extra formulas for z because, it's still z, right? So these 2 coordinate systems share the coordinate z. Really a lot like just polar coordinates. A couple of quick examples. You can persuade yourselves. I'm going to leave this as an exercise, but if you just write down the equation r equals c, what this is saying is we're looking at all the points whose distance from the z-axis is a fixed constant c. And I think it's a pretty easy pitch that that's a cylinder. And by the way, which is the motivation for the name cylindrical coordinates. Okay. A little bit of algebra, and it's not hard to persuade yourself that the cylindrical equation for a sphere is this. And of course, y'all remember this was the equation for a sphere from rectangular coordinates. So, in cylindrical coordinates, equation just looks a little bit different. Again, I think that's a pretty easy pitch. One that is easy to mess up is this one here. You look at the equation z equals kr, and a lot of people, again, have grown up for whatever reason thinking that r, must be positive, and that's not the case. And for example, in this equation here, certainly z can be negative. Well, if z is negative, then so is r, right? And so we have to consider all the values. There's different ways that you can think about how I get this picture here. My favorite is to observe that this has no thetas in it. And if this equation has no thetas in it, then it shouldn't matter what theta is, which means that in that plane for a given fixed value of theta, and in, let's say this plane for a different value of theta, right? So we have there two different theta planes. Well, different thetas, but the theta isn't in the equation. So these cross sections should look exactly the same. Right? No thetas means it doesn't matter what theta is. You get the same answer no matter what theta is. And what do you get for each of those values of theta? Well, looking just kind of in one of those theta planes at a time, I think it's a pretty easy pitch that this is just a line of slope k. Right? And so now imagine what happens when you look at that in all planes. Namely, what happens if you rotate this line around the z-axis, and well, you get this cone here. So you get that rotated around gives you a cone. All right. Okay. A real quick warning. We are all accustomed to using R as a, for in high school algebra anyway, as being the radius of something. Right? If you're given something and, it's a sphere of radius R, or, something like, cylinder of radius R, what have you. Do be careful about that now, because R is now no longer just a regular letter of the alphabet. Now it's a variable. I mean, imagine this. Imagine if you were to talk about, well, I've got a circle of radius X, and I'm going to look in the XY plane at blah, blah, blah. Whoa, hey, slow down. You just confused your variables. You're using X now as a coordinate, and you're also using it to represent a constant describing something you're interested in for whatever reason. And that's a confusion of variables. So heads up, if you're going to use, if you have a radius that you need a letter for, you just can't use little r. Now what you can use, perfectly fine, you can use capital R, no problem. You can use R naught, fine, right? Any sort of variation, but you just can't use little r by itself. That's no longer up for grabs. That's now a variable. All right. Okay, let's see. And I guess we have 2.5 minutes left. Real quick, I'm going to start off in defining spherical coordinates. This one is weird. It's got two angles in it, distinguishing it from cylindrical and polar, each of which only have one angle. We use the two angles to define a direction, and once you define the direction, then we talk about a distance in that direction. But let's not get ahead of ourselves. We're going to start off with theta. Oh, you know what? Bad color choice. Theta is going to define what I'm going to call a half plane hinged on the z-axis. So theta defines, in polar coordinates, theta defines a direction. Right? But since there's also up and down, theta now defines, and I suppose I should extend down below as well, defines a direction, defines a half plane of all points who from the z-axis are in that direction. All right, is everybody good? Very importantly, this is a half plane, not a full plane. Okay. Now, within that half plane, I'm going to talk now about this angle called phi, which tragically is written in a way that's not that different from theta, which leads to all sorts of confusion. I don't know why they made that choice, but it's extremely standard. So we're kind of stuck with it. Anyway, phi. And it's the angle measured off of the positive part of the z-axis, and very importantly, measured toward the theta half plane. Right? So it doesn't go back this way. That would be a negative value of phi. Right? So positive values of phi are in the direction toward the theta half plane. Is everybody with me? And now I argue that with theta and phi both defined, notice that defines then a direction. And once you have a direction, then just like we did in polar coordinates, once you have a direction, then you can talk about how far, air quotes, how far to go in that direction, and that leaves you at a point, defining that point in space. And again, with the how far, what if it's negative? Well, if it's negative, then you just go backward instead of forward. Everybody happy? All right. And I'm out of time. So we will call it a day right there and pick up here on Wednesday. Y'all have a good rest of your Monday. See you later.